Welcome to the lecture on equivalent circuit of the three-phase induction motor. Here we will be talking about derivation of the equivalent circuit and the considerations for stationary and rotating rotor. What are the changes taking place in the equivalent circuit, and the phasor diagram for the based on the equivalent circuit, and then how you could refer the equivalent circuit to the stator side, and then power flow equations and determining equivalent circuit parameters. So the equivalent circuit of a wound rotor induction motor at standstill can be represented from this kind of a circuit, where Rx is the external resistance connected between slip ring and the neutral, which means we are talking about like per phase circuit. And R2, this is obviously the rotor side. R2 is the rotor winding resistance per phase, and then Jx2 is the rotor leakage reactance. This is rotor leakage reactance, and then T is an ideal transformer with turns ratio 1 to 1. And then we jump across to the rotor stator side. On the stator side, we got Rm representing sorry, this must be M, external resistance connected between this one resistance corresponds to iron loss. Sorry, I made a mistake. Rm is there. Rm is the resistance corresponds to the iron loss in the stator, and Xm is the magnetizing reactance of the stator winding, and Jx1 of course is stator leakage reactance, and R1 is the stator winding resistance, and Eg is the source voltage line to neutral, that means phase voltage. So this is a per phase equivalent circuit for a three-phase induction motor. And then those who remember the equivalent circuit of a transformer that we derived in your second year, or if you have read about it in a power engineering course, then you will remember that this is pretty much the same when the motor is at standstill. But there are changes when the motor starts to move, and then we also could do a few approximations to the equivalent circuits. These are also some of the approximations that we did in the equivalent circuit for the transformer. What we do is this combination, parallel combination of Rm and Xm, we move it to the beginning, which makes the analysis of the circuit pretty much easier. Magnetization current block is moved to simplify equivalent circuit reduction. The remaining electrical circuit can be reduced to a simple series circuit element. Let's see how we could do it. Now when the motor is running, suddenly what happens is, to the right of the transformer we got a different frequency. Because of that, we multiply the quantities from S, the slip. Frequency dependent impedances like inductance, reactances, inductive reactances, they change the value. Resistances remains the same. Voltages are multiplied from a factor of S. So if you could see here, frequency is F on the stator side, still F, but frequency on the rotor side is SF. The frequency of the voltages and currents in the stator is F, but frequency of the voltages and currents in the rotor is SF. And then the equivalent circuit of the rotor, if we consider only that, then it is got a voltage source which has a magnitude of S times E1, and then there is a reactance of JSX2, and the total resistance of the rotor circuit can be lumped together and expressed as R2. So what we got basically is a simple RL circuit supplied by an AC voltage. Therefore, obviously, the current should be lagging in phase. So that is what has been demonstrated in the phasor diagram. SE1 is the supply, the voltage, rotor induced voltage, and the current I2 in the rotor is lagging by an angle beta. Beta is can be calculated from the magnitudes of the inductive reactance and the resistance. E2 and I2 have frequency SF. The equivalent circuit of a wound rotor motor referred to stator side. So just like the way we reduced the or simplified the transformer circuit, we could do the same thing to eliminate the ideal transformer in between. But when you do that, you have to compensate um, for the difference in frequency. So that is done by simply by dividing R2 from S. The lumped rotor resistance should be scaled by slip. X2 goes S times X2 is reflected as J just X2 without S. Rest is the same. So the ideal transformer is gone. The circuit is becoming much more simpler. Then what? The power flow. Power flow in the motor, you can easily calculate the following things using the circuit. Those all those equations are in the textbook. You can find active power, reactive power, and apparent power absorbed by the motor, power factor of the motor, line current, active power supplied to the rotor, power loss in the rotor, mechanical power supplied by rotor, torque in rotor. Those things can be calculated using these circuit parameters. And you can further simplify the circuit by eliminating the magnetizing circuit block, particularly when the machine is loaded. As far as mechanical power, torque and speed are concerned, Xm and Rm can be neglected. That is because just like in case of the transformer, we neglect the magnetizing circuit when the transformer is loaded up to the rated levels, rated conditions, simply because the current going through the magnetizing circuit is comparatively less than the load current. So we do the same simplification, and then you end up with a simple resistor inductor RL circuit. Now phase diagram when motor develops maximum torque. Now the typical phasor diagram for this kind of a circuit will be like this, where you get the supply voltage or the supply voltage, and the current is lagging to the supply voltage. So the current as well as the voltage drop across R1 and R2 divided by S will be in phase with the current I1. So you get this current I1 times R2 over S, and then I1 times R1, both are in phase, they add together, and then the voltage drop across X reactance, lumped reactance, equivalent reactance will be in perpendicular to the this voltage drops in the resistive parts. So that goes up like this, and finally the resultant should meet the end tip of the vector or the phasor EG. So under these conditions, when the torque is maximum, what should happen is R2 divided by S should be equal to Z1. Z1 and R2 divided by S should be equal. So you got a triangle with these two sides equal. That is the maximum point. In other words, sometimes in circuit theory you may have learned that the you can, if you think of these two as the source impedances of the this voltage source, you know that if the external load impedance is equal in magnitude to the internal source impedance, you get the maximum power output. So that is exactly the same theory that we are using here. So if these two sides are equal, then the power becomes maximum. So the breakdown torque can be calculated at this condition. So that is how the phasor diagram will look like when the motor is developing the maximum torque. And then we should also talk a little bit about measuring equivalent circuit parameters. These two to me are pretty much equivalent to the no load test and the short circuit test of a transformer. Now the no load test is like it's called the no load test, and it permits to calculate XM and RM, same as in case of a transformer. No load test gives rise to XM and RM can be found. And equivalent to short circuit test of the transformer, what we've got here is the locked rotor test. Locked rotor test permits the calculation of the total leakage reactance X and the total resistance R1 plus R2. From these results, we can determine the equivalent circuit of the induction motor. Locked rotor test, X and R in the stator and rotor can be found. But just like in case of a short circuit test for a transformer, you got to use a reduced voltage for this test, for the locked rotor test. That's an important thing. So in summary, the three-phase induction motor equivalent circuit is very similar to that of a transformer with one small adjustment, that is replacing the load impedance with a speed dependent resistor. That's the main difference. There shouldn't be a bullet point here, sorry. From this equivalent circuit, the power flow can be calculated. Maximum torque occurs when the impedances have equal magnitude. This corresponds to the breakdown torque and explains the shape of the torque speed curves when rotor resistance varies. The equivalent circuit parameters of a three-phase induction motor can be measured using no load and locked rotor test, similar to open circuit and short circuit test for the transformer. Sorry about a couple of unnecessary bullet points, but that is a summary of what we discussed in this lecture. Thank you.